Fundamentals of Artificial Intelligence. Artificial intelligence, or AI, refers to systems designed to mimic human intelligence. Machine learning, or ML, is a subset of AI where systems learn from data. Deep learning represents an advanced form of ML that uses multiple layers of neural networks. Neural networks are computing systems inspired by the way biological brains work. AI systems use computer vision to understand and process images and use natural language processing, or NLP, to comprehend and process human language. Artificial intelligence serves as the broadest category in this hierarchy. Machine learning functions as a subset of AI that specifically focuses on learning from data. Deep learning represents a specialized type of machine learning that employs neural networks. The key distinctions between these concepts lie in their approaches. AI can include rule-based systems, ML requires data to learn patterns, and deep learning needs large amounts of data and computing power to function effectively. A model is a mathematical representation trained on data to make predictions, while an algorithm is a step-by-step procedure for solving problems. Training involves teaching AI models by using data, and inferencing is the process of using trained models to make predictions. Bias refers to systematic errors in AI systems, while fairness helps make sure that AI systems treat all groups equitably. Fit describes how well a model performs on data. Large language models, or LLMs, are AI models specialized in processing and generating human language. Types of inferencing and data. Types of inferencing. Batch inferencing involves processing multiple inputs simultaneously, and is typically used for non-time critical applications, making it more efficient for large-scale processing. In contrast, real-time inferencing processes one input at a time, providing immediate responses, which is crucial for applications such as autonomous vehicles. Types of data. When considering data labels, we have labeled data, which comes with known outcomes, and unlabeled data, which lacks predetermined outcomes. In terms of structure, data can be either structured, appearing in organized formats such as databases and tables, or unstructured, existing as raw data such as images and text. Data formats. Various data formats exist in AI applications. Tabular data resembles spreadsheet-like information. Time series data consists of sequential data points. Image data encompasses visual information. Text data includes written or typed content. Audio data comprises sound information, and video data consists of moving images. Conclusion. Artificial intelligence represents a transformative field encompassing various specialized areas, from its broadest form as AI to machine learning and deep learning. The field processes data through different methods, including batch and real-time inferencing, while handling various data formats from tabular to multimedia content. Key concepts such as models, algorithms, training, and inferencing form the foundation of AI systems. Considerations of bias and fairness make sure these systems remain ethical and equitable in their applications. An introduction to Amazon Bedrock. Overview. Amazon Bedrock is a fully managed service that offers high-performing foundation models, or FMs, from leading artificial intelligence companies such as Amazon, Meta, Mistral AI, Anthropic, Stability AI, and Cohere. All these models are accessible to developers through a single API. Amazon Bedrock provides the capabilities to build generative AI applications with security, privacy, and responsible AI policies. With Amazon Bedrock, you can experiment with and evaluate top models, customize them using private data, then build agents that run tasks across your business systems. Because Amazon Bedrock is serverless, there is zero management of infrastructure and can be integrated into applications using familiar AWS services. Benefits. Model evaluation. Amazon Bedrock provides the ability to evaluate, compare, and select the best model with automatic evaluation, using metrics such as accuracy and toxicity, or use human evaluation for subjective criteria such as style, brand, and domain knowledge. Customization. Amazon Bedrock supports fine-tuning, with labeled data, for certain models from Cohere, Meta, and Amazon, Amazon Nova text models can be adapted to your industry and domain using continued pre-training without the need for labeled data. When customizing a model using fine-tuning or continued pre-training, Amazon Bedrock makes a separate copy of the base FM to create a private model. Retrieval Augmented Generation, or RAG. Amazon Bedrock allows you to enhance models with current and proprietary information using knowledge bases or KBs. KBs couple a text embedding model with a vector database, such as Amazon OpenSearch Serverless, to augment LLM prompts for more accurate responses. Features: security and privacy. Amazon Bedrock keeps your content safe by using encryption at rest in the same AWS region and is not shared with the outside world. Amazon Bedrock supports compliance standards such as SOC, ISO, HIPAA, and GDPR. For extra security, you can also use AWS Private Link to connect your VPC resources to Bedrock endpoints. Guardrails. With Amazon Bedrock you can implement safeguards based on your corporate policies by configuring guardrails to filter inappropriate content, redact personally identifiable information or PII, and monitor violations. Agents. Amazon Bedrock agents allow you to plan and run complex multi-step tasks by integrating with your systems and data sources. Agents help automate tasks such as making API calls, engineering prompts, and overall orchestration of your generative AI pipelines.
Generative AI Overview. Generative artificial intelligence, or generative AI, is a form of artificial intelligence that has the ability to create various types of content, including conversations, stories, images, videos, and music. Generative AI relies on large machine learning models, known as foundation models, which are pre-trained on extensive datasets. Foundation models have billions of parameters and have experienced significant growth in size in recent years, with the largest models now exceeding 500 billion parameters. Foundation models, such as GPT 3.5, Bloom, and Stable Diffusion, are versatile and can perform a wide range of tasks across different domains. They can write blog posts, generate images, solve math problems, engage in dialogues, and answer questions based on documents. Amazon provides several offerings in the field of generative AI. Amazon Bedrock. Amazon Bedrock streamlines generative AI by providing an accessible API for foundation models from AI21 Labs, Anthropic, Stability AI, and Amazon. Using Amazon Bedrock, developers can efficiently build and scale generative AI-based applications, which opens the technology to a wider range of users. Machine Learning Hub. Amazon SageMaker and Amazon SageMaker Jumpstart are valuable tools for customers seeking flexibility in machine learning model building. SageMaker Jumpstart serves as a machine learning hub, offering a wide range of open-source foundation models for exploration and deployment, including OpenLLM, RedPajama, Mosaic MPT7B, Flan T5/UL2, GPT-J6B/Neox20B, and Bloom/Bloomz. Amazon Q Developer. Amazon Q Developer uses a foundation model to enhance developer productivity by generating real-time code suggestions based on natural language comments and prior code in an integrated development environment, or ID. Computing infrastructure. AWS offers machine learning infrastructure that prioritizes cost efficiency and performance. AWS Trainium and AWS Inferentia chips were specifically developed to work, providing the lowest cost options for machine learning tasks.
Training and fine-tuning AI models. Fine-tuning methods. Instruction tuning teaches models to follow specific commands and generate appropriate responses. This involves training on carefully crafted instruction response pairs. Domain adaptation focuses on specializing models for specific industries or use cases, such as healthcare or finance. Transfer learning uses pre-trained knowledge for new tasks, while maintaining general capabilities. Continuous pre-training helps make sure that models learn from new data while retaining existing knowledge, keeping them current and relevant. Data preparation. Data curation is critical for fine-tuning success. This involves selecting high-quality, relevant data that aligns with intended use cases. Governance helps provide proper data handling, including privacy compliance and ethical considerations. Dataset size requirements vary by task, but quality often matters more than quantity. Careful balance between too little data, or underfitting, and too much data, or potential overfitting, is essential. Data labeling must be accurate and consistent, whether done by experts or through crowdsourcing. Representativeness helps make sure the dataset covers all relevant scenarios and user groups, minimizing bias. Special attention must be paid to edge cases and diverse examples that reflect real-world usage. Regular data quality assessments help maintain high standards throughout the fine-tuning process. RLHF and quality assurance. Reinforcement learning from human feedback, or RLHF, improves model outputs based on human preferences. This involves collecting human ratings of model responses and using them to refine the model's behavior. RLHF helps align model outputs with human values and expectations. Continuous evaluation and feedback loops helps make sure the fine-tuned model maintains desired performance levels. Encoder and decoder LLMs, unlocking the power of language understanding and generation. Introduction. In the rapidly evolving world of natural language processing, or NLP, the rise of large language models, or LLMs, has revolutionized the way one interacts with and understands language. At the heart of these powerful models are the encoder and decoder architectures, each serving a distinct yet complementary role, built upon the transformer architecture. Transformer architecture. The transformer architecture is a fundamental advancement in NLP, enabling the development of highly expressive and versatile language models. This architecture is based on the attention mechanism, which a model can use to selectively focus on relevant parts of the input sequence rather than processing the entire sequence uniformly. This attention mechanism enables the transformer to capture long-range dependencies and effectively process sequential data, such as natural language. Encoder LLMs. Encoder LLMs, such as bidirectional encoder representations from transformers, or BERT, use the transformer's encoder component to excel at language understanding tasks. These models are trained on vast amounts of text data, so they can develop a deep comprehension of language, including its syntax, semantics, and contextual nuances. Encoder LLMs are particularly adept at tasks such as text classification, named entity recognition, and question answering. Key features of encoder LLMs. One of the key features of encoder LLMs is their bidirectional nature, which they use to consider the context of a word or phrase from both the left and right sides. With this bidirectionality, the model can better capture the complex relationships and dependencies within language, leading to more accurate and nuanced understanding. Encoder LLMs also use attention weights, which highlight the relevance of different parts of the input text to the task at hand. To preserve the information about the word order in the input sequence, encoder LLMs use positional encoding. This technique adds positional information to the token embeddings, making sure that the model can understand the relevance of each word's position within the sentence. Encoder LLMs often employ masked language modeling, where the model is tasked with predicting the masked or missing words in the input text. This approach encourages the model to develop a deeper understanding of language structure and semantics because it must infer the missing information based on the surrounding context. Multi-headed self-attention. Another important aspect of the transformer architecture is the use of multi-headed self-attention. In this approach, multiple sets of attention weights, or heads, are learned in parallel, each capturing different aspects of language. This way, the model can develop a more comprehensive understanding of the input with different heads potentially focusing on entities, activities, or other linguistic properties. Decoder LLMs and key features. In contrast, decoder LLMs, such as a generative pre-trained transformers, or GPT, use the transformer's decoder component to focus on language generation. These models are trained to generate coherent and contextually relevant text, making them highly useful for tasks such as text summarization, dialogue systems, and creative writing. The key feature of decoder LLMs is their ability to generate text one token at a time, based on the previous context. With this sequential generation process, decoder LLMs maintain coherence and consistency throughout the output, making sure that the generated text reads naturally and logically. Conclusion. The transformer architecture, often referred to as the encoder-decoder architecture, has been a game-changer in the field of NLP, enabling the development of highly expressive and versatile language models. These hybrid models use the strengths of both encoder and decoder approaches to handle more complex language tasks, such as machine translation, text summarization, and question-answering systems. Generative AI, pros and cons. Advantages of generative AI. Adaptability is a key strength of generative AI, which can learn and adapt to new contexts and tasks with minimal retraining. Responsiveness helps provide real-time interaction and dynamic content generation based on user inputs. User-oriented implementation means organizations can deploy solutions without extensive custom coding. These models can handle multiple tasks by using the same base architecture, making the models versatile for various business applications. They excel at understanding context and generating human-like responses, making them valuable for customer interactions. Disadvantages and limitations. Hallucinations are a significant concern of generative AI. Models can generate plausible but false information. Interpretability remains challenging as it's often unclear how models reach specific conclusions. Inaccuracy can occur, especially in specialized domains or with complex queries. Non-determinism means the same input might generate different outputs each time, making results unpredictable. These limitations require careful consideration in critical applications, where accuracy and consistency are paramount. Selection factors of generative AI. Model type selection depends on specific use cases, such as language models for text and diffusion models for images. Performance requirements include response time, accuracy, and resource consumption. A capabilities assessment involves understanding what the model can and cannot do effectively. Constraints such as computing resources, budget, and deployment environment must be considered. Compliance requirements, including data privacy and regulatory standards, are crucial selection factors. Business values and metrics. Cross-domain performance measures how well the model handles various tasks and industries. Efficiency metrics track resource utilization and response times. Conversion rates show how effectively the AI drives desired user actions. Average revenue per user helps quantify financial impact. Accuracy measurements help provide reliable performance. Customer lifetime value indicates long-term business impact. These metrics help organizations justify investments and optimize implementations. Conclusion. Generative AI offers powerful capabilities that require a strategic organizational approach. Its adaptability and responsiveness provide business advantages, despite challenges like hallucinations and interpretability issues. Model selection should evaluate type, performance, capabilities, constraints, and compliance factors. Business value metrics include cross-domain performance, efficiency, and customer lifetime value. Organizations can use generative AI's benefits, while managing its risks to create meaningful business impact.
Machine learning overview. Machine learning, or ML, is the process of teaching a machine or a computer how to perform a task such as identifying fraudulent credit card transactions. Before machine learning, using classical programming, developers spent many hours creating logic rules and applying them to a specific dataset to calculate an answer. Now with machine learning, developers can create computer algorithms that can learn from experience without relying on rules-based programming, thereby moving the heavy lifting away from humans and onto machines. Machine learning is good at solving problems, like predicting the price of a book, based on its features, such as the number of pages, the author, and whether it has a hardcover or not. It also excels at solving classification problems like determining whether a movie review is positive or negative. Machine learning components. Data. The data to solve a machine learning task consists of features and a label. Feature data are the inputs, or X variable, the known attributes about the problem your task is trying to solve. Label data is the output, or Y variable, the value or attribute you are trying to predict. ML data types can be either categorical such as a movie genre, or numerical such as a book price. Algorithms. A machine learning algorithm is a set of instructions a computer runs to determine the rules that allow it to predict a label or output in a dataset. There are two types of machine learning algorithms. Supervised ML algorithms use data with labels, or the observed output, already included with the feature data. Supervised ML algorithms are suited for solving problems involving linear regression and classification. With unsupervised ML, the labels are not provided as part of the input. Unsupervised ML algorithms are better at solving clustering problems that find naturally occurring groupings. Machine learning lifecycle. The machine learning lifecycle involves determining the business problem with goals that are specific and measurable, defining the machine learning model by rephrasing the problem using ML terminology, and then identifying the type of algorithm that is best suited for the task. The next step is to prepare the data, which requires gathering, merging, and cleaning up features and label data. Once the data is ready, you train and test the model and tune hyperparameters until the desired accuracy is achieved. The final step is to deploy the model to production and then evaluate it to improve the predictions by iterating over the previous steps.
The AI model lifecycle. Overview. The foundation model lifecycle consists of several critical stages that work together to create effective AI systems. Starting with careful data selection and preparation, the process moves through model selection, pre-training, and fine-tuning phases to develop specific capabilities. The deployment phase and continuous feedback loop help make sure that the model remains effective in real-world applications. This systematic approach demonstrates the interconnected nature of creating successful AI systems that meet both technical and business requirements. Data selection and preparation. Foundation models begin with careful data selection. This involves gathering diverse, high-quality datasets that represent the model's intended use cases. Data must be cleaned, validated, and properly formatted. Key considerations include data diversity, bias mitigation, and ethical sourcing. The quality and breadth of training data significantly impact the model's final capabilities. Model selection and pre-training. Selecting the appropriate model architecture is crucial. Factors include model size, computational requirements, and intended applications. Pre-training involves teaching the model general language understanding, or domain knowledge by using self-supervised learning on large datasets. This phase requires significant computational resources, but creates a versatile base model. Fine-tuning and evaluation. Fine-tuning adapts the pre-trained model for specific tasks by using smaller, task-specific datasets. This process enhances the model's performance for particular applications, while maintaining its general capabilities. Evaluation involves testing the model's performance by using various metrics, including accuracy, response quality, and task-specific benchmarks. Multiple evaluation rounds help make sure that the model meets both technical and business requirements. Deployment and feedback loop. Deployment involves integrating the model into production systems, with appropriate scaling and monitoring solutions. Continuous feedback collection from users and system metrics helps identify areas for improvement. This feedback loop informs future model iterations, data selection, and fine-tuning strategies. Regular monitoring helps make sure that the model maintains performance and adapts to changing requirements.
Bedrock.